Hi guys, in this video let us talk about the type of membership functions. There are several subsections in this as well. The first one is we can form certain membership functions by using straight lines. So let us have a look at them. So the first membership function that you might come across in your textbook would be called as a triangular membership function. As the name suggests, it looks like a triangle, the one that you can see on the screen, and it is defined by using three parameters A, B and C. So B is the parameter which decides what would be the pinnacle point in your membership function, that is the point which would give you 1 as your membership value, and A and C would define the points where the membership function value would be 0. So the definition is present over here. So if x is less than a, you would be getting a value of 0, and then if it is between a and b, then you have an increasing line, that is the slope is always increasing, and between b and c the slope is decreasing, and if the x value is greater than c, then you can clearly see that it's again 0. Now an extension to your triangular membership function is your trapezoidal membership function, and instead of just having 3 parameters, this time around you would be having 4 parameters. So this would be A, this would be B, this would be C, and this would be D. I haven't written the definition for it here, but I guess you guys can pretty much figure out what this is talking about. If you compress this trapezoidal membership function, it would turn out to be a triangular function. Straight line membership functions are not always useful. The reason being they're not continuously differentiable. So what do I mean by that? So if you look at a straight line like this, if you try to measure the slope at this point, I'm talking about this point, let us say this point is A, and let us look at another point called B. If you take the slope at this point and then this point, the slopes would both be the same ones. Now, there can be certain cases where our slopes differ, as in if you take a curve like this, so over here the slopes can differ. Now we can create certain membership functions like that as well, and then they'll definitely serve our purpose. So we need to look ahead, like go beyond our straight line membership functions, and the first one that you would find in that category is a Gaussian distribution function. The definition for that is given on your screen. It is e raised to minus x minus b whole square divided by 2a square. As you can clearly see, it has two parameters, a, which I have marked on the screen, and then b, which is also marked on the screen. So a typically tells you which is your half point in the case of increasing trend of slopes, and b marks the midpoint of the decreasing trend of slopes. Another membership function that you have in this category is called as a generalized Bell membership function. The definition for that is given over here. As you can see, it has 3 parameters, A, B and C, which define the way the curve goes. One advantage with this curve is that it is never 0. So we are talking about only values which are greater than 0. So that is sort of like reducing our effort. And the second characteristic that we have with this Bell membership function is that it can approach a non-fuzzy set if the third parameter, that is C, is tuned. So somehow if we can like tune this particular parameter C here, it will become a non-fuzzy set, sort of like a crisp set with which we can perform a lot of operations much more better, in a much more better manner. A downside to this is we cannot specify asymmetric membership functions using this. Now, if you can recall from the properties of membership functions, I have already told you that the membership functions have this property of symmetry with it. So symmetry is something like this. So you have a curve like this, you take a midpoint, and then if you look at this left half and the right half, if they are mirror images of both of them, of either of them, then you might call it as a symmetry. So there can be certain membership functions which do not have to like go ahead with this property, and this is where our generalized Bell membership function or your Gaussian distribution function or your straight line functions fail. So let us have a look at a few functions which are good at that. So let us try understanding these asymmetric membership functions by the help of the first example here. It's called as a sigmoidal membership function, and the definition is over here. I'm not sure the denominator over here is clear. It is 1 divided by 1 plus e to the power minus a into x minus c. This is a minus. This is not an implication. This is a minus. Anyway, so a is over here and then c is over here, as you can clearly see. So if a is greater than 0, the curve always keeps increasing from left to right. So this is the point I'm talking about. And then when a is less than 0, that is over here, then the curve decreases from left to right. So that is not clearly specified in our graph over here. But if you were to like elongate this, so this would like look like this. So it would look like something like this. And C is called as a point of inflection. So what does this do? It technically tells you the point where the graph stops increasing, because you cannot go beyond 1. Your values always have to lie between 0 and 1. So that is a point where it stops increasing and then it starts taking a constant trend like this. There's another small nomenclature associated with this. This graph, the one that you're looking at here, is called as open from right. The reason why it is called so is pretty much clear in your picture. If you look here on the left hand side, I mean, you could erase this part, and this is all not there. I just drew it to help you guys understand. If you can look at it clearly on the left hand side, the graph looks like it has been closed on one end, but on the right hand side it looks like the graph just keeps going on. There is no stopping to it. So if you look at a graph like that, it is called as open from right. In some cases it is even called as open to right. So the words are used interchangeably. And using this sigmoidal membership function, you could create more different kind of membership functions. So how do we do them? You club 2 or more sigmoidal membership functions in order to like get them. The first graph that you're looking at, the one over here, this is obtained by subtracting 2 sigmoidal membership functions. And as you can clearly see, this graph doesn't have an open end to it. So it is called as a closed membership function. It is not open from right or open to left. And this graph, the second one that you are seeing right here, this is obtained by multiplying 2 sigmoidal membership functions. And as you can clearly see, this sort of looks like it is symmetrical, but this one is definitely asymmetrical. So if this were the middle point, this is definitely showing you that they are not mirror images of each other. The next category of membership functions are called as polynomial based curves. The first subsection under this is called as a Z-shaped function. The definition of it is given over here. It clearly has 3 parameters in it, A, B and C, and you guys can like take up a minute to try figure out what is happening in this curve. Let us try understanding the different properties that it has. Now, as you can clearly see, if you were to like draw a straight line across the middle point, the left half and the right half, they are not mirror images of each other. So this is clearly asymmetric in nature. Also, you can clearly see that the left part here is pretty much open when you compare with the right part. Right part is like converging towards 0, whereas the left part is hovering around 1, which is a higher value. And then this membership function, it is usually used to associate with words like poor, weak or short. Now poor, weak, short, they all define some very low values. So why do we use this membership function to define some low values? If you try understanding how this particular graph is working, you'll understand why we're using this for such low values. If you can look at this graph, until 0.5 is the point where the graph keeps having higher values, or it has a trend of values changing. The moment it reaches 0.5, the values, they sort of go near 0. That is over here, you can pretty much see that the values are nearing 0. So since we have a lot of variability in this particular part, that is the first half or the lower parts, this membership function will be really useful for any word that defines a very low value, like these. Let us look at another function. This is called as an S-shaped function. Once again, the definition for this is over here. You guys can have a look at it. And this is exactly the opposite to your Z-shaped function or Z-shaped function. As you guys might have already guessed, this is used for all strong words, like all big words: old, tall, rich, and strong. And another property that you could associate this with this graph is it is open towards right, and left is like pretty much closer to 0. So this is open towards right. The next membership function in this category is called as a pi function. It is also called as a spline based curve. The reason why it is called as a spline based curve is because of this structure. So whenever you find a structure which is like this, it's called as a spline based curve. This is a general notion. There is no specific membership function definition to it. Now vicinity function is a membership function which makes use of this pi function. So pi function is sort of like the generalized function here. And as you can see, it has a couple of parameters A and B. And another speciality to this vicinity function is that it uses the S-shaped function in turn in its own definition. B is called as a bandwidth, and 2B, as you can clearly see here, it is the distance between 2 points in the curve which are zeros. So that is called as a bandwidth. So the actually mattering parameter would be this A. Now let us look at the different methods for determining membership functions. We are done with them. So let us try understanding how people would actually come up with which membership function to use in which particular condition. The first method is called as a subjective evaluation and elicitation. So this is a general method. So what experts would do in this case is they would like employ different people, maybe like come up with statistics based on people being young or tall or short, and then they come up with graphs based on that. So this is just subjective evaluation of, so it's sort of like taking a lot of statistics and then working based on that. The second is called as converted frequencies or probabilities. So what people would do in this is they would look at whatever definitions they have in probability theory and then somehow employ a method to convert that into a membership function in the case of our fuzzy sets. Now that translation is not directly possible because we already know that probabilities and fuzzy sets are two different things, but people have worked around this thing. So this is also definitely possible. The third one is called as physical measurement. So if people use some kind of physical devices to like come up with certain values, so that kind of method is called as physical measurement. The fourth one is called learning and adaptation. This would be closer to your understanding. The reason being, you come up with a random function and then you try tweaking the parameters in it and then try understanding how well the function actually suits the values that are given in your data set. So this is actually closer to your ML. So ML's application is definitely over here.